welcome to my lecture series on advanced linear algebra. We have already seen some linear operator are diagonalizables, but most of them are not diagonalizable. I mean, one can find out in order basis corresponding space under which the operator can be represented by a diagonal matrix, or the matrix is similar to a diagonal matrix please. But it is not true for the most of the cases. So, what is the next simplified form? We are looking for that one please. So, for that let me introduce one terminology that is called invariant subspace. So, what is that? What is invariant subspace? Let me define it. Invariant subspace. Let T be a linear operator on a vector space V over the field capital F. A subspace W of V is said to be invariant under T, provided for all alpha belongs to W, T of alpha belongs to W. That is, your T of the entire W will be subset of W. Then only I can say that the subspace W of the vector space V is invariant under T. For example, let T be a linear operator from V to V. The linear operator that I am denoting as LO from V to V. Then RT, that is range space of T, and NT, that is null space of T, are invariant under T. How? Okay. For any beta belongs to RT implies that there exists alpha belongs to V such that T of alpha equal to beta, and also T of beta will be in the range of T, will be also in the range of T, because it will be either if T of beta equal to 0, then also beta will be in the range space, because range space is subspace. So, it must include 0. If T beta not equal to 0, then by default T beta will be in the RT place. Similarly, if alpha belongs to NT, this implies that T of alpha equal to 0. So, this implies T of alpha belongs to NT, because NT is also, since NT is also a subspace of vector space V. So, by default we see that range space as well as null space of the operator are invariant under T. Let me take other examples. Again consider the same, let T be the linear operator from V to V. Consider W equal to 0 subspace, that is 0 subspace. What can I say about this 0 subspace? Whether will it be invariant under T or not? Certainly it will be. Yes. Then we see T of 0 equal to 0, that is the property of the linear operator. So, this implies T of 0 also belongs to W. So, this implies W equal to 0 is also invariant under T. Now, if I consider W equal to the entire space V, what can we say about this ones? Then also we have T of V is a subset of V. So, this implies that W equal to V is also invariant under T. So, they are all trivial examples. Now, let me consider some examples which is not trivial, please. So, this is say example 2, this is example 3. Let V be the space of all polynomial functions over the field capital F. So, we know V is a vector space. Let W be the space of all polynomial function over F of degree less than or equal to n. So, this implies that W is a proper subset of V. Now, consider the differential operator D on V. Then W will be invariant under D. How? For any P belongs to W, P will be of the form of like A naught plus A1 x plus A2 x square plus A n x to the power n, where AI belongs to capital F, because a polynomial function of degree less than or equal to n. So, P will be of this form. So, this implies when the differential operator D operating on P will be equal to what? It will be A1 plus 2 A2 x plus 3 A3 x square plus n x to the power n minus 1. Will it belongs to the W? So, it certainly belongs to W. So, this implies that W is invariant under D. Okay. So, let me consider another very interesting results and interesting examples like this. Let T and U be two linear operator on vector space V, which is defined over the field capital F. I am not talking about the dimension of the vector space V please here, it may be finite, infinite, whatever it may be like that. The operator T and U such that T and U satisfies the relation, that is, or a property you can say like that, T U equal to U T. I mean to say the operator T and U, that commutative, then the range space of U and null space of U are invariant under T. How? So, let us quickly check how the range space of U will be invariant under T. Let W equal to range of U. So, let alpha belongs to W. So, this implies that there exists beta belongs to V such that U of beta will be equal to alpha. So, this implies when T operating on alpha, this will be equal to how much? T of U of beta, and this is equal to T U operating on beta. So, T alpha equal to T U operating on beta, which is same as U T operating on beta, since T U equal to U T. So, this implies that U of T of beta. So, T alpha equal to U of T of beta. So, this will be certainly belongs to range space of U, that is W. So, T of alpha belongs to W. Okay. So, you see that range space of U is invariant under the operator T please. Similarly, one can check that W equal to null space of the operator, null space of U is invariant under T. This is I am giving as a homework please. Okay. So, we have seen couple of examples of invariant subspaces. Let me give another very standard examples which I shall use it frequently in the coming lectures. So, therefore, let me introduce that one also. Let T be a linear operator on a finite dimensional vector space V over the field capital F. Let C be an eigenvalue of T and W be the corresponding eigenspace. So, this implies that for any alpha belongs to W, T of alpha equal to C alpha. So, this implies W is invariant under T. So, eigenspace of a linear operator is always invariant subspace of that operator please. Now, let us see what way this concept of invariance will helpful to understand the characteristic polynomials, minimal polynomial of the operator please. So, let T be a linear operator on a finite dimensional vector space capital V over the field capital F. Let W be a subspace of V which is invariant under the operator T. Let V star equal to alpha 1, alpha 2, alpha k be an order basis, of W. So, I can extend B star by adding some more linear independent elements of V to be a basis for the entire space V. So, let B consisting of alpha 1, alpha 2, alpha k plus 1 to alpha n be an order basis of capital V. Since T of alpha I belongs to W for I less than equal to k. Now, when I represent, so implies for T of alpha I when I less than equal to k can be represented by the order basis element alpha 1 to alpha k only. So, I need there are only k scalars say a 1 I, a 2 I, a 3 I up to a k I such that T of alpha I equal to can be written as sigma a k I T of alpha j can be written as something like I j I equal to 1 to k only and alpha I, because W is the invariant under T. So, that is why image of T alpha I less than equal to k I will be able to express with the basis element of W. So, T alpha j will be basically linear combination of alpha 1 to alpha k only. So, I need only k scalars, and for j greater than k, T of alpha j will be written as say a I j alpha I equal to 1 to n please. So, here I need to express alpha j by the basis element of the vector space V. So, I need n constant. So, this implies the matrix representation of T with respect to this order basis B. So, this will be equal to of this form, I will have a some square matrix here, say B matrix and C matrix, 0 matrix and D matrix, where B is K cross K matrix over F, C is n minus K cross K matrix over F, and your D is, it will be n minus K cross n minus K square matrix over this one please. So, the matrix representation will be like this thing. So, if I simplify it, let me introduce one more operator defined like this. Let T w, I mean I want to induce a linear operator on W, that is T w, let T w be a function from your W into W defined by T w of alpha equal to T alpha for alpha belongs to W. So, this implies that T w is a linear operator on W, which is called as restricted operator on W. I mean basically restricted operator of T on W please, of T on W. So, T w is nothing, it is a basically W induce a linear operator which is a restriction of T on W, that is restricted operator of T on W please, that is T w please. So, we have the matrix representation of T w will be what? The matrix representation of T w with respect to the order basis your B star, that is alpha 1, alpha 2, alpha k, B star is nothing, you are simply B matrix. Space. So, one can write down the matrix representation of T with respect to order basis B is nothing, the matrix representation of T w with respect to B star and C matrix, some other matrix D and 0. So, it is like this thing please. So, the structure of the matrix representation of this operator, suppose if you denote this capital A, then capital A is like this thing please. This implies the characteristic polynomial of T, that is determinant of x I minus capital I. So, determinant of x I minus capital I is nothing, it is basically I can write down minus 1 to the power n B minus x I, this is I means I k, k by k identity matrix please, this one, and then this C matrix I will have 0 D minus x I n minus k cross n minus k please, this one, this k I k cross this one please. So, determinant of this quantity please. So, this is basically equal to, I can say, determinant of x I k minus b into determinant of x I n minus k minus d. So, this implies if characteristic polynomial of T w is q x and characteristic polynomial of capital A is say f x, then q x divides f x please. So, characteristic polynomial of restricted operator T w divides characteristic polynomial of A. Now, what can you say about the minimal polynomial of T w and minimal polynomial of the A? Is there any relation between these two minimal polynomials? Now, to answer these questions again, so let us see what is different power of A. Now, question is, if P 1 and P 2 denote minimal polynomial of A and B respectively, then is there any relation between P 1 and P 2? That is the question. If P 1 and P 2 denote minimal polynomials of A and B respectively, then is there any relation between P 1 and P 2? See, for this we have capital A equal to what? We have A equal to B into C, for let me for sake of simplicity let me get C 1 0 and D matrix. So, then what about A square? A into A will be equal to A square will be equal to how much? This will be again B C 1 0 D into B C 1 0 D. This will be equal to B square into some other one, this one C 2 and 0, and you can see the structure will be like these things. So, A square equal to, I will have the entries are B square and this component, this will be basically some other matrix, that is k cross n minus k, this is C 2 matrix please, but it will be, and this other diagonal entry will be D square. So, diagonal entry will be B square and D square, but the off diagonal will be 0 and some other matrix C 2. So, in general you will have A to the power r equal to, I will have B to the power r some C r 0 and D to the power r. This implies if P 1 is minimal polynomial of A, so P 1 of A will be equal to 0. So, this implies P 1 of B also will be equal to 0, but minimal polynomial of B is given P 2. So, that is the least degree monic polynomials which annihilate B. So, this implies P 2 must divides P 1, P 2 must divides P 1 please. That is minimal polynomial of B must divide minimal polynomial of original matrix A please. So, we have seen that if W be a invariant subspace of a vector space V, then it simplifies the matrix representations. It also helps to understand the characteristic polynomial, minimal polynomials, and you will see it has many more applications to simplify the operator. Now, let me consider examples. Let T be a linear operator on R2. Let the matrix representation of T with respect to standard order basis of R2 be say capital A, which is equal to, let me write down, 0 minus 1 1 0. Then R2 has 0 subspace and R2 itself are only invariant subspaces, invariant subspaces of R2 under the operator T. Here I have considered T be linear operator on R2, certainly R2 over R, I mean field is the real number please. I have to show that for this case the only subspaces which are T invariant or invariant under T are the 0 subspace and R2. Certainly 0 subspace and R2 are invariant under T. Let W is a proper subspace of R2. Proper subspace of R2, if possible let W be also invariant under the operator T. So, this implies for any alpha belongs to W, T alpha will belongs to W again, being proper subspace of R2, certainly W has to be a one dimensional subspace. Certainly dimension of W equal to 1. So, this implies any non-zero vector say beta, any non-zero vector beta belongs to W will act as a basis of W. So, this implies W equal to linear span of beta. So, this implies if I consider alpha belongs to W, alpha will be equal to of the form of something C beta, and if I say that T of alpha will be in W, so this implies that T of alpha equal to again I mean something like D into beta type. So, this implies alpha equal to C beta. So, this implies that I can write down beta is equal to 1 by C times alpha. So, T of alpha can be written as D into 1 by C into alpha. So, it is equal to D by C into alpha. Let me consider alpha not equal to 0. So, 0 not equal to alpha if you consider, then certainly alpha equal to C beta means C not equal to 0. So, T of alpha equal to like this thing. So, this implies that T of alpha is equal to sum T times alpha, T belongs to F. So, this implies T is an eigenvalue of the operator T, but T does not have any eigenvalue, because since characteristic polynomial, that is x square plus 1 is not factorizable, over the field R. If W is invariant under T, then W cannot be a proper subspace of V place. But if you change suppose if I consider the operator T, instead of defining over R2, if I consider C2, then this corresponding matrix is remain same, but it will be then I will say that there will be a proper subspace which will be also invariant under T, because in that case you will have eigenvalues as plus minus I, and you will get the corresponding eigenspace which will be T invariant. So, we will continue to use this concept of invariant subspace for simplification of the operators. So, that will be done in the next class please.